Okay, today we're going to talk about thermal statistics. This tends to be a fairly mysterious topic. Um, like I said earlier, the cool thing about thermodynamics is that it's not intuitive, that by understanding thermal statistics and thermodynamics and how to do the math, you can figure out things that aren't obvious. But before we talk about thermal statistics, I want to go back and talk again, just review molar heat capacity. Remember we discussed that each degree of freedom in a molecule contributes 1/2 nRT to the energy of the system. So the internal energy is just going to be equal to NCV delta T. Okay, once again, really what it's equal to is N times the number of degrees of freedom over 2 times R times the temperature, right? That's the internal energy. And it just so happens that C sub V is equal to the number of degrees of freedom over R. All right? Why? Because each degree of freedom adds this much to the thermal internal energy of the system. So for a monatomic gas, there's only 3 degrees of freedom, and C sub V is just 3/2 R. All right? C sub V in general is the number of degrees of freedom over 2 times R. So for a monatomic gas, there's only 3 degrees of freedom. For a diatomic gas, just to review again, I have these two atoms. They're kind of bound together. In addition to translation, they can also rotate this way, or they can rotate out of the screen like this. Rotating around their axis doesn't count because quantum mechanics tells us that that type of rotation, there's a symmetry there, and you don't notice, right? So that type of rotation is actually taken care of doing physics differently. So we only get 2 degrees of freedom that break the symmetry of the system. So we get our 2 additional degrees of freedom for rotations that go along with our 3 kinetic degrees of freedom for 5 total degrees of freedom. And so for a diatomic gas, the molar specific heat at constant volume is 5/2 R. Okay? So there's a review. Now I'm going to show you, I went and looked up the specific heat of a bunch of different materials, and I put them on this bar graph so you can see. Here is the specific heat, joules per kilogram degree C, or Kelvin. All right, and you can see they're all over the place. Hydrogen has an extremely high specific heat. Water and ice have very high specific heats. All right. Lead, not so much, and so forth. Anyway, you get this broad spread. But instead of thinking in terms of the specific heat per unit mass, or sorry, the heat capacity per unit mass, which is the specific heat, let's think in terms, not in terms of capacity per unit mass, let's think of heat capacity per mole. All right, so to do that, I go through and find the molar masses of all these different things, and I come up with this plot right here. And you can see things are much more consistent here. All of these solids have very similar molar specific heats. You look at these gases, they're similar. Methanol's kind of goofy. Why is it goofy? Let me change my scale now. Instead of plotting this in terms of joules per mole Kelvin, I'm going to plot it in terms of R. All right? If I make that conversion, it looks just like this. All right? So for most of my solids, the molar specific heat is pretty close to 3R. All right? It turns out that solids tend to have 6 degrees of freedom. All right? If we look at our gases, nitrogen and oxygen and hydrogen, they all form diatomic molecules. So that should be 5 degrees of freedom. The molar specific heat should be 5/2 R. And if you look at this, 2.5. That's 5/2 R. So pretty close to 5/2 R. Ammonia has a bigger molar specific heat. Why? It's got more degrees of freedom. Carbon dioxide has more than 2 atoms, right, in the molecule, so it has more degrees of freedom. Methanol is huge. Why is methanol huge? It's a big floppy molecule with lots of degrees of freedom. So I found this was very enlightening, just showing that the physics that we're learning actually works in real life. Now notice these aren't exactly 5/2 R, and that has to do with quantum mechanics and thermal statistics, all right? It turns out it takes a finite amount of energy to do certain excitations in a molecule. Quantum mechanics tells us that a molecule can't have an arbitrary internal energy. It's quantized. And so collisions that excite different types of excitations, if they don't have enough energy, they can't excite certain excitations. All right, so this has to do with, then, thermal statistics. How fast are my atoms in this gas coming together when they collide with each other? Can you turn on these degrees of freedom, or do these degrees of freedom not really count? And that's what this comes down to. What the molar specific heat will be for a given gas depends on the temperature, because the temperature determines how many atoms are moving at certain velocities, okay? So, now we're moving on to thermal statistics. How do I calculate how many atoms are moving near some velocity? All right? Well, there's this thing we call the Boltzmann distribution law, and we're not going to actually use this much in this class, but this is where the equation we will use is derived from. All right? And it basically says this. All right? And here, if we take a quantum mechanical approach such that energy levels are quantized and atoms can only have certain energies, if I take some energy level at some energy E, the number of atoms that will be, or the number of molecules that will be in that energy state, is equal to this. G is the density of states. All right? It says, or I guess the number that will be at a given energy will depend on how many levels there are at that energy, because in a quantum mechanical system you can have two different states that happen to have the same energy. So this thing here is the degeneracy. How many different states have that same energy, and then you multiply by this thing here known as the Boltzmann factor. All right? But we have not learned quantum mechanics yet, so let's consider sort of a classical interpretation. If I'm doing classical physics, it really doesn't make sense to ask how many atoms or how many molecules have a particular energy E, right? Because in classical mechanics, molecules can have any energy. It's a complete spread, right? They're not just specific energies they can have any energy. So how many energy possibilities are there between 0 and 100 joules, for example? There's an infinite number, right? You can add any arbitrarily small amount of energy and get to a new energy. So it doesn't make sense in classical physics to ask how many atoms will have some energy E. It just doesn't make sense. None will, right? If I say how many atoms in this room have a thermal internal energy of 1 joule. All right? If you go and you find me one, I'll say, no, look closer. And you'll find that, oh, it's not really 1 joule, it's 0.9999997 something joules, right? If you look closely enough, you'll find it's not exactly at the energy I asked for. So at any given energy, there are no atoms at that energy. So what does this equation even mean? It should always be 0, right? Well, in a classical interpretation, this equation means something different. Instead, what n as a function of energy is it's the thing that I multiply by some little small amount of energy, and that will tell me how many molecules have an energy E, which is within dE of E. Does that make sense? So if I were to plot this function n as a function of energy, whatever it turned out to be for my system, all right, the way that I would find out how many molecules there are near some energy is by integrating this, all right? So basically, I integrate n dE from some energy 1 to some energy 2, energy 1, energy 2. All right, I do that integral, and the integral then is what tells me how many molecules have an energy between energy 1 and energy 2. So it doesn't make sense to ask how many molecules have a certain energy, because there's an infinite number of energies they could have. But it does make sense to say how many atoms in this room have a thermal energy between 1 and 1.0001 joules, right? And so in the classical interpretation, this thing never really appears alone. It always has to have this little dE that goes with it. It's something that shows up in an integral. All right, so with that in mind, here's the equation that the book gives you for the distribution of velocities. So instead of thinking in terms of energy, now let's think in terms of velocities. How many atoms in this room, how many molecules, are moving with a velocity of 100 meters per second? And the answer is, of course, none of them, right? None of them are going to exactly be moving at 100 meters per second. You might find one that's really close, but it'll be a little bit more or a little bit less than 100 meters per second, because there's an infinite number of possibilities, right? Between 99 and 101 meters per second, there's an infinite number of possibilities, an infinite number of velocities the atom could have. It could have velocity of 99.5, 99.6, 99.61735, right? So the probability of actually finding any molecule in the air in the room you're in being at exactly 100 meters per second is 0. It doesn't make sense to ask about an individual velocity. So what does this equation really mean? Well, this is the thing we put into an integral and integrate from some velocity A to some velocity B to find out how many particles there are that have a velocity between velocity A and velocity B. All right? Now, this is exponential in velocity. All right? So if the temperature is higher, we get more molecules at higher velocities. So if you look at this plot, the blue line represents a gas at a lower temperature, and the magenta line represents a gas at a higher temperature. Okay, so at the higher temperature, there's fewer at lower velocities, but there's a higher number of molecules at higher velocities. And that makes sense. As I heat the gas up, more thermal energy, more kinetic energy, that means I should expect to find more molecules at higher velocities and fewer at lower velocities. Now, if you look in your book, the equation that is given in your book doesn't look exactly like this. Instead of this thing A, it has a big thing here that depends on the mass of the molecules and the temperature and so forth. All right? But I chose to leave that out and just call it all A. Lump all that stuff together, A. And what A really means is, all that stuff in front of there, if I take this thing and I integrate, NV dV, and if I integrate from 0 velocity to infinite velocity, that means I'm finding how many particles there are that have a velocity between 0 and infinity. That should be all of the particles. All right? So all this stuff that's in front of this equation in your book, it's really just a normalization constant. It's the thing we have to put in front of the interesting physics such that when I do this integral, I get the actual number of particles, the total number of particles. All right? So that's what n sub v is. All right? It's a thing that when I plot, it doesn't tell me, right, if I look at this plot and I look right here at 600 meters per second, it looks like it's about 12. That does not mean that there are 12 particles traveling at 600 meters per second. That means that there's a large probability of finding particles in a range near 600 meters per second, right? This is something that we put into an integral and integrate. All right? Now, there's some parameters that we talk about. There is, if I take this plot, if I take this equation here with the actual stuff here for my normalization constant, I can look at that and I can say, well, what is the most probable velocity for an atom to have? All right? The most probable velocity. Okay, there are no atoms at any specific velocity, right? I mean, but what is the velocity that if I look at it, if I integrate near that velocity, I will get the largest number of particles? Near what velocity is the distribution the biggest? That's what it's really saying. V most probable. That's just where this equation is the biggest. All right? So you see this red line right here marks V most probable. It's just the peak of the distribution. All right? But then there's also the average velocity and the RMS velocity. All right? So what's the difference between most probable and average? Most probable is just the top of the distribution. But if I average the velocity, if I take all the particles in the room and calculate the average of their velocity, I'm not going to get the peak of the curve. I'm going to get kind of somewhere where on this side, if I integrate under the curve, I get half the particles, and if I integrate on this side of the curve, I get half of the particles, right? So to find the average velocity, what I do, to find an average, I just add things together and then divide by the number of things I added by, right? So I'm going to take the velocity of each particle. Let's say I have n particles in the room, all right? I'm going to take the velocity of each one. I'm going to take the magnitude of that, right? We don't care about the x or y components. We just care about the magnitude of the velocity. I add them all together, and then I divide by the number of particles, right? That's going to be the average, all right? Well, when I have a continuous distribution, I have so many atoms, I'm not thinking in terms of individual atoms anymore, and I'm using my distribution function then. What I can do is I can say, well, how many atoms are there between some velocity a and some velocity b? All right, that's just nv dv, right? So how many, okay, so I'm just going to multiply by the velocity, right? And that's how many atoms there are near some certain velocity times that velocity, right? And then I'm going to integrate that from 0 to infinity. So I'm weighting my integral with the velocity, right? And so that will give me kind of a weighted average, but in the end then I have to just divide by the total number of particles, which also happens to be equal to this, right? So by doing this integral, nv dv, and dividing by n, that will give me the average velocity, all right? Whereas the most probable is just where my distribution is the tallest, all right? So to find the most probable, I just take the derivative of this thing with respect to velocity, and I set it equal to 0, and I can solve for the most probable velocity, all right? So that's the idea here. V average is the average velocity of all the particles in the room. Most probable is just the peak of the distribution. Then we have this thing called the RMS average. What is the RMS average? RMS stands for root mean squared. So the idea is instead of summing up all the particles, so V average would be I sum the velocity of all of the particles and then I divide by the number of particles, right? Okay, that didn't look very good. Let's draw that again. So to find the average velocity, I just sum over all of the velocities of all of the particles, this is the magnitude of their velocities, and divide by n, right? And in RMS, what we do is we sum the squares of something, right? So to find the RMS velocity, we would be summing this here, right? So x is just some generic thing. You can find the RMS of anything. The RMS of a voltage, RMS of a velocity. If I'm specifically finding velocity, then the equation would look like this, right? I'm summing up the squares of the velocities instead of the velocities. So this right here is not the average velocity, it's the average of the velocity squared. Then once I take the average of the velocity squared, I take the square root of that. And that's what the RMS means. RMS, the root mean square, means I take the average of something squared and then I take the square root of that. Alright? So for example, imagine I wanted to take the RMS value of this list of numbers. Alright? The first thing I do is I square them all. I get 9, 16, 49, 1, 3, and 4. Alright? Then I add them all together and then divide by the number of numbers, right? There was 1, 2, 3, 4, 5, 6 numbers. So this right here is the average of the squares. It's the average of the numbers squared. And I just take the square root of that, if I take the square root of that, that gives me the RMS average. All right? What is the average of these numbers? Well, the average, the regular old plain average, I just sum them up, right? So 3 minus 4 is minus 1, plus 7 is 6, 7, 8, 9, 10, 11, 12. So it's just going to be 12 divided by 6, so it's going to be 2. So the average is 2, but the RMS is a little bigger than 2, right? It weights the bigger numbers more, essentially. All right? But that's what an RMS is. An RMS is the average of the squares, then take the square root of it. All right? Now, why do we care about RMS? Why does RMS matter? Well, oftentimes what we care about is something that scales as the parameter squared, right? For example, dealing with gases. The kinetic energy of a molecule is not proportional to the velocity, it's proportional to the velocity squared. So if I wanted to know what fraction of molecules had enough energy to get over some barrier, for example, I wouldn't care about the average velocity of my gas. I'd care about the RMS velocity, the RMS average of the velocities of the atoms in my gas. So that's why RMS matters. Now, thermal statistics turns out is really important. It's kind of abstract, but it shows up all over the place. For example, if you're a chemist, doing a chemical reaction in a gas phase. Maybe there's a reaction barrier. Maybe the molecules repel each other, and only if they get close enough to each other, they can overcome this repulsion, do they actually bond together and do a chemical reaction. So there's this repulsion, but if the molecules have enough velocity, they can overcome that repulsion, get close enough together for the chemical reaction to occur. So how fast the chemical reactions occur will depend on the thermal statistics. It'll depend on how many atoms are traveling faster than some velocity. In atomic physics and lasers, oftentimes you wonder how many atoms are in a given state, right? If I'm going to make a laser, I need to know how many of them are in the excited state and how many of them are in the ground state, right? If I have my laser beam being absorbed by atoms, atoms in the ground state will absorb the light, atoms in the excited state will actually be stimulated to come back down to the ground state and give off more light, all right? So we need to calculate how many atoms are in a given state. Doppler broadening. You remember the Doppler shift? If I look at the spectrum of a gas of atoms, I find that the natural resonances in the atoms will actually be broadened because the atoms are moving. I need to know how fast they're moving, how many of them are moving at different velocities to understand that Doppler broadening, right? Collisional frequency. How often do atoms bump into each other? Depends on how fast they're going, how many of them are going at different velocities. In my graduate work, I worked on something called quantum degeneracy, where we actually cooled atoms down so cold that they basically all went into the same quantum state. Once they're in the same quantum state, they stopped behaving independently and behaved like one giant mega particle. All right? Well, to understand quantum degeneracy, you need to know the thermal distribution of energies amongst your atoms. So anyway, thermal statistics, it's kind of abstract, but it turns out to be really useful in a lot of different ways.